My name is Mazhar Ali, and I am an associate professor in the Quantum Nanoscience department here at TU Delft, and also part of the Kavli Institute for Nanoscience at Delft. My research group works on what we call the 3 Qs: quantum materials for quantum properties and quantum devices, which are very important for next-generation technologies. I was 3 years old when the Berlin Wall fell, but a few years ago I had the opportunity to walk part of the Berlin Wall Trail, which really impressed upon me how people and ideas were segregated at that time, and how imagination and creativity were severely suppressed, which is so important for societal as well as scientific progress. Our group's breakthrough was to make one-way superconductivity without needing any kind of external help, like a magnetic field. Superconductivity is one of the most interesting and mystifying subjects in all of physics. Despite over 100 years of investigation, we still don't have a complete understanding of how it works. It's a phenomenon where below a certain temperature, a material suddenly loses all of its electrical resistance, meaning it can conduct electricity indefinitely without any loss of energy. It's the basis for a lot of important technology, ranging from MRI, magnetic resonance imaging, all the way to quantum computing and the superconducting qubit. But superconductivity has always been two-way, meaning if it's superconducted to the left, it's superconducted to the right. It was demanded by symmetry to be so. To make superconducting electronics in analogy to semiconducting electronics, which are the basis for basically all modern technology, we needed to overcome the barrier of making something superconduct in just one direction. So principal researchers, Drs. Hengwu and Yaojie Wang, created a simple device where we joined together 2 superconductors across a quantum material that itself broke symmetry and allowed left to be different from right. You can think about it like a special kind of ice, where if you're skating in one direction, you have 0 friction, but you have insurmountable friction going the other way. This behavior is akin to a diode, where, as you can see in the image, independent electrons, shown in orange, flow in one direction, while superconducting pairs of electrons, shown in green, flow in the other direction. This leads to the creation of superconducting electronics, including computers, that can operate hundreds of times faster than current electronics, while also being greener, consuming only a fraction of the amount of energy used today. The next step is to optimize the materials and conditions in order to make billions of devices per chip. Our hope for the future is to overcome the terahertz speed barrier. For the past decade, computers have been stuck operating at just a few gigahertz using semiconductors, but with one-way superconductivity, we have a new starting point to begin increasing processing speed again. My passion is to bring superconductivity into the mainstream. I believe that if the 20th century was the century of the semiconductor, the 21st century will be the century of the superconductor.